Hello. Nice to meet you at the session 7A, System Engineering, Computer Technology. I am Jevgenijus Toldinas from Kaunas University of Technology. And now at that session we have 5 presenters. So every presenter will have 18 minutes, including discussion. After 15 minutes I will show you that and one. Okay? So the first presentation will make Krzysztof Okarma and adoption of full reference image quality assessment methods for automatic visual evaluation of the surface quality of 3D printers. Please.
Okay, thank you, Mr. Chairman, for your nice introduction. As you said, my name is Krzysztof Okarma. This is the paper which was written together with my PhD student, Jaroslaw Fastowicz. It is strictly related with the topic of his PhD, which is related to quality assessment, visual quality assessment of 3D printed surfaces. Well, a short outline of my talk is shown here, so I will try to briefly introduce the topic and the quality issues in additive manufacturing. I will try to remind you some metrics which were presented yesterday, so this would be very short, and I will tell how would it be possible to make the metrics blind, because blind metrics will be necessary to use in this problem. Some discussions and results. Well, as you know, 3D printing is one of the most rapidly growing technologies nowadays. It's widely used in biomedical engineering, but not only in biomedical engineering. There are numerous applications in industry. If you want to produce some parts, even electronic circuits. Yesterday there was a presentation by Linas Vilanis about the circuits which are built on the 3D printed plates, as very similar to ours. So the quality is very important. Of course, you can try to check the internal structure of the 3D printed parts, but we focus on the vision. Why? Because our aim is to correct the 3D printed surface even during printing if possible. So if we mount a camera, we can not only monitor the progress of printing, but also try to correct some small issues or just abort the printing process in case of detected very low quality, just to save the material, to save the energy and time as well. So that's our aim. Of course, we can try to assess the quality of the surfaces also offline after processing. So it could also be useful for assessment of some parts, for sorting, classification of some already printed elements. There are 4 most popular methods of 3D printing, including selective laser sintering, inkjet printing, stereolithography, and fused deposition modeling, which is the cheapest and the most popular, so we focus on this because some quality issues take place usually in FDM printers. So there are numerous such printers, you can buy it easily. Some exemplary issues, overfilling or underfilling, let's say dry printing, it's also called like this. The presence of some cracks can occur in such materials, and of course there are some reasons for this. The main sources of such problems, quality issues, are related to the quality of the filament itself, because it could be very cheap and not very high quality. Of course, the quality of the printer, or quality of the materials from which the printer was made, sometimes on your own. And sometimes some distortions may occur during the printing process. They can be improper temperature, for example, not according to the type of the filament, and so on. So we forced some issues to make some bad quality samples, changing the temperature, changing the movement speed of the filament, changing the configuration of stepper motors, their rotation, and so on. So we obtained different images. They were scanned using a flatbed scanner. They have been also photographed by a camera. You can observe each layer of the filament. So our idea is to mount the camera in such a way that it will be the side view location. So we will observe the printed surface from a side, not from the top, because our aim is not to monitor the progress of printing. This is already done. Our aim is to monitor the quality. So we observe the regularity of layers. On the left side, we can observe quite high quality sample and lower quality sample of different color filament is shown here. So we should classify the samples into low and high quality. Regardless of color, it is not done in this paper, it's not color independent, but we used some other methods as well, which are color independent. So our final aim will be to combine some approaches together. Exemplary applications, well known, so I will skip this slide because of limited time. In art, robotics, chemical industry, food industry, there are many, including biomedical engineering, many applications. Ideas of working selective laser sintering based on powder and laser, similar to normal printer. Inkjet printing allowing to paint somehow the surfaces. Stereolithography, also based on the laser and the liquid, which hardens according to the laser light. And the most popular fused deposition modeling. If you buy a roll of filament, you can melt it and form according to the motion of the nozzle, layer by layer in different structures. You can buy a lot of printers on GPL licenses. It's not very expensive. Sometimes $100, $200, $300. It's not a very expensive thing. Some researchers have used vision in 3D printing, but not for quality monitoring, for the monitoring of the process, or even if it was related somehow with quality monitoring, it was not purely visual. There were no features used, no regularity assessment, but just the comparison of two neighboring layers, for example. Are they similar or not during the printing, assuming the top view camera. So some attempts have been made, sometimes using neural networks, sometimes just only for fault detection, sometimes using probably the most recent idea from 2015 by Jeremy Straub from one of the American universities, the use of image analysis for detection of the lack of filament during the printing. But well, to be honest, the system based on 5 Raspberry Pi units and 5 cameras was very unstable, very sensitive to changes of lighting conditions, to even small motions of cameras. So it was just something in progress, just a good idea, but maybe not finished, far from industry. And there was nothing at all related directly to the quality assessment of 3D prints. So knowing some methods related to general purpose image quality assessment, maybe some of them could be useful also for this purpose. We have some printers, quite cheap, 3 of them. This one is a bit more professional, so we had some devices to develop, make some samples. Well, we had discussed during yesterday's lecture some full reference image quality metrics. Most of them are based on similarity of some fragments of images. Their disadvantage is that they require the knowledge of the original image. Here, we don't have the original image. If we assume that this is just the first sample we print, we do not know the original, we do not want to make a model. We have the model, but it's hard to compare the print with the model. What to compare? 3D cloud of points, shapes, or something? It is possible, but we focus on surfaces, and the surface is just a surface. So we have to think about the surface as a texture. So if some of the metrics produce the local similarity indexes, we assume that if we take a fragment of the 3D printed part, if it is high quality, it should be similar to the other fragment of the same part. If the quality is low, if there are some issues, probably they are located somewhere else into parts. So we can divide our part into some fragments and calculate the similarities using some of the methods. I will just remind you very briefly. For example, structural similarity, multi-scale structural similarity, complex wavelet structural similarity could be useful for this purpose, structural texture similarity, feature similarity, and so on. The idea is to calculate the mutual similarities, dividing the image representing the 3D printed surface into several parts. Well, we assume the division into 4 parts, 9 parts, or 16 parts. Not more, because if we divide it into smaller parts, there will be a lot of mutual similarities to calculate, so it will be too slow. 4 parts may be too less, so the question is how many parts should be to have a reasonable classification. For 9 parts, we have much more calculations, and if we divide into 16 fragments, we would have 120 mutual comparisons, so it will be a bit slower to calculate. So we assumed that if we mount the camera on the side, if we force the presence of some distortions, we can try to adapt such full reference image similarity, I would say, approach to our problem. So the first thing we should think about is the phase adjustment. Because if we would have 2 fragments of an image, maybe not neighboring in horizontal direction, but in vertical direction, if the first line of the first row of our part will represent the darker part of the layer, and in the second part the brightest, the similarity will be low. So we should adjust the phase of each layer, sometimes just to cut a half or a bit more of one layer. So, but if we have, even if we have 4x4 matrix of fragments, there will be several layers, because each layer is represented by maybe 15, maybe 16, maybe 18 pixels, so it's large enough. Okay, so We divided this, if we have 1600 by 1600 resolution, so it's large enough to calculate such similarities. And we made over 100 samples of different colors using two types of filaments, PLA and ABS, assessed them manually into high quality, moderately, low and low. But we classify only to high and low quality. Moderate is just for the discussion if it is close to the border or not. So, as I said, all the images were captured and subjectively assessed by our colleagues, converted into grayscale because the metrics are dedicated for the grayscale images, and results for 16 blocks for structural similarity. Some of the samples have cracks, so they have empty symbols. The round, more round are high quality, more rectangular are low quality samples, so they are mixed here. So structural similarity is not good for this. PSNR, peak signal to noise ratio, is also not good because they are somehow mixed. How to assess even maybe the pink samples? They are mixed. If we use feature similarity for only 4 blocks, we have more or less the same problem, but okay, it is better. It is easier to separate. We have some problems here with the red, the green samples. We have some problems for silver samples, some problems for maybe for brown it's okay. So it is quite acceptable, but for 16 blocks, there are almost all samples properly classified. For each color, I can find the threshold between the round and rectangular shapes. Only 4 or 6 samples are a bit troublesome, but they are moderate quality. So, if we verify this using well-known classification metrics like specificity, F-measure, or accuracy, high quality and low quality are true and false. Samples we classify as true positives, false positives, and so on. So wrongly classified samples are considered as falses. So if we discuss this, we can observe after calculations that the overall accuracy is about 97%. So as I said, maybe 6 samples are incorrectly classified, but the disadvantage is that we have to know the color of the filament, because without this knowledge, we wouldn't know how to set the threshold. So this method is good, but dependent on color. F-measure is also quite high, and in future we would like to combine this approach with some other approaches. We have investigated some methods based on the half transform for line detection after binarization, histogram of oriented gradients, entropy, and some other methods. So we would like to combine them into a hybrid metric, and it should be color independent. Our approach based on the entropy was color independent for a bit lower number of samples, about 80. So probably after the combination with this, it will be better than a single approach. So probably just in time. Thank you
for your presentation. And let's have discussion. Questions? I have one question. Because you analyzing visual images, is there an ability to use your methods for detecting steganography footprints, where in images inserted text?
Well, if you would like to apply such methods to detect some hidden information, there are two issues. It depends on the type of the steganography, and if this is the image which is stored, for example, a grayscale image, if it is stored on using more than 8 bits, you can try to analyze this if you have appropriate camera, because human eye can distinguish not more than 100 shades of gray, so 7 bits would be enough. So 8-bit could be used for steganography purposes, and if the camera would be deep enough, if you consider the number of bits, you can try to use some similarities, but you should have a flat surface, flat by means of similarity. So if you would like to hide some information and some text in such images, it could be found, because the similarity would be a bit lower if you detect something. But if you would have just a natural image of, I don't know, of a landscape or something, there is no self-similarity between the fragments of the image. So only for such images when the self-similarity of the fragments is expected. But if you would like to use the steganography on lower quality images, it will be probably impossible to detect using such methods, because there are some lower similarities caused by the low quality of the surface.
Okay, thank you. Thank you.
Thank you.
So the next presentation, Musaed, Togacar, and subclass separation of white blood cell images using convolutional neural network models. Yes.
Thank you, my predictions. Thank you, my predictions. My predictions commonly of deep learning and biomedical images title subclasses separations of white blood cell images using convolutional neural networks models contains of 6 chapters. My predictions commonly biomedical image and after deep learning models. What are white blood cells? What is the white blood cell produced in the bone marrow and lymphocyte tissue in knuckle and as leukocyte, and then in important part of immune system to protect the body and against foreign invaders and infected disease. Fourth separates subclasses as eosinophil, lymphocyte, monocyte, and neutrophil. This test commonly everyday hospital information about WBC is microscopic blood image of patients play important role many disease diagnosis and management of WBC blood type in the human body is one of the most important parts immune system and plays an important place in body fight against bacteria and virus, and in microscopic in human body approximately 4,000 and 10,000 adult human body having values outside specific range leads various diseases such as anemia, liver diseases, bone marrow defect disease, leukemia, tip disease disease. The reason of this disease deficits or excess of VABC cells. Why did we use the deep learning models? We analyzed this biomedical image classifications of ABC with deep learning model. A lot of clinic experience for a doctor detect amount WBC human blood and classify it. It is important to use time efficient and diagnosis correctly because this test commonly daily made up. Dataset train test validation 3 olmaktadır. 75% train, 20% test, 5% validations. For tip white blood cells in the human body contains of H image data consists of deep 24 bits and resolution of 30 120 and 240 pixels. The file examines of DCOM conversations JPEG image format. Dataset and hardware correlate. Softmax classifier percent 30 dataset. We used the data test data and 70 training data. For other classifier 10-fold cross validation used in the dataset. The dataset is completed, GPU supported. My computer software 64-bit Windows 10 operations and GPU hardware NVIDIA GeForce 2 graphics cards and Intel E5 Core 5 GHz processor and 8 GB RAM contains of. The validity of study related specificity and accuracy positive, sensitive and true negative, false positive, false negative are used to calculation measurement. CNN models 4 tips, 3 tips and 2 tips used to software LeNet, AlexNet, VGG16. Image size are same as but learning rate different and mini-batch same as. Optimizations ADAM, SGD and RMC probe used to Otur operamentler selected default birinci first method general 2 methods selected in the first method AlexNet FGG16 and LeNet models were used to Python software. The best performance is AlexNet gives accuracy and features after features classifier 4 tips white blood cells tips classifier analysis is first method classification results AlexNet AlexNet accuracy 84 47 AlexNet based query, success rate, graphics query and epoch, train and verifications source. Third, second method without classification, deep learning models, SVM, softmax, nearest neighborhood, QDI, decision tree, sports vector machines, linear discriminant analysis, classifier used the method. This results quadratic discriminant analysis base query rate 9778. Other class Lampatic 99% success rate. Confusion matrix overall success rate calculation of confusion matrix values for classes. The graphics of ROC, curve and confusion matrix obtained from QDA classifier is given figure 4. Success rate and base query source. Other comparison with other models using the same datasets, query 90 and 91 approximately sells it. My our models is AlexNet is base query 97 success rate results shown in table base 5. Comparisons and with other models and results before tables and same as. In this study we have classifications. We double BC image on the subcategories with preset methods, feature extraction and classifications, process, performance, deep learning model, and other models. Features deep learning models after other models based recurse based query results using made of and base results performance of achieved QDA classifier rate of 97%. Thank you for listening. I speak English bad. I am sorry. I am panicking.
Thank you for your presentation. Let's start discussion. Questions? So I have one. As you present, JPEG images was 320, 240, yes?
Yes.
But in the model, as I see, there were 2027 and 2027. You are snipping that image. Is quality depends on that?
Repeat after me.
Could you, from start? From second one? Oh.
Yes.
32 or now second slide? Yes. Till second table. Oh, sorry. Oh. One image size.
Conversations. My same as models comparisons of without image size. My other other hyperparametry
For accuracy,
comparisons.
it's not accuracy the same was with that image size and that you firstly show us.
I am not sure. Deep learning models of default image input size 227 and same as made up models tested via conversations image size.
The images was converted, yes?
Yes.
Okay, thank you.
Sorry.
Questions? So, thank you for your presentation. Next presentation, Borisas Lozinskis, MQTT quality of service versus energy consumption.
Hello, dear colleagues. Hello, everybody. I'm Borisas Lozinskis from Kaunas University of Technology, and today I'm going to introduce you our presentation, MQTT quality of service versus energy consumption. So, outline is as follows. Some words for the beginning of MQTT protocol. Of its quality of service and energy consumption, then modeling energy consumption of the quality of service levels of MQTT protocol, our case study and experimental results, and then finally conclusions. Now at this moment, as you know, several standard machine-to-machine application layer protocols are used to interconnect the things an application, such as message queuing, telemetry transport, constrained application protocol, extensible messaging and presence protocol, and then finally web application messaging protocol. MQTT, which was researching in our experiment, has a low memory footprint, low power consumption, and better distribution of information to recipients. Its simplicity, reliability, three quality of service levels, resource constraint support makes MQTT very popular in Internet of Things. MQTT is a lightweight asynchronous protocol which model based on publish-subscribe sequence. It allows, in fact, devices to exchange data by using a message broker. The broker not only pushes message data to the subscribed customers, but additionally stores it, forwards, filters, and prioritizes a publish request from the publisher to the subscriber. MQTT provides three levels of quality of service. At most ones, the message is the lowest level. The message is sent to subscriber only once. At most ones, it's not stored in publisher, does not receive any information about message delivery. Sometimes it's called fire and forget. The second one, at least once, the message is sent to the subscriber at least once one time, and an acknowledgement procedure is used in that level. If publisher does not get an acknowledgement, other publisher attempts to send message to subscriber will take place. And the highest one, exactly once, a level of service is used to ensure safety and guarantee the message delivery. During publishing the message, 2 rounds of transmission are used. So, according to an energy consumption and battery life, MQTT and quality of service domain is depicted here because energy consumption of Internet of Things with low energy and battery level is a critical point. Quality of service level must deal with it. As we can see, at least one and exactly one's levels have the potential to decrease the battery life, and only the lowest level has the potential to increase the battery life. Here in proposed model we evaluate reliability requirements in terms of MQTT quality levels with energy consumption due to the nature of Internet of Things systems, where energy consumption plays very important role for the system's lifetime. Now about our case study and experimental results. We have used Wi-Fi router, Raspberry Pi, a module of Internet of Things ESP, digital multimeter, and lithium battery as power supply for ESP module. To investigate the energy consumption of MQTT levels of quality of service, we employed Raspberry Pi and ESP and connected them through the Wi-Fi router. Raspberry Pi and ESP module act as two end nodes of the network that are located at a distance less than 1 meter from each other and Wi-Fi router. We conducted our experiments in standard room condition. In case of our experiment scenario, ESP module is generating data packets as a publisher. At the same time, it is receiving data packets as a subscriber. On the other hand, Raspberry Pi is playing broker role. It receives the data packets from the publisher and forwards received data packets to the subscriber. Here all technical specification of both devices are presented and the way they were connected between each other. Now at this figure we can see the battery voltage level, how it was decreasing for every MQTT quality of service levels, for at most ones, at least ones, and exactly ones. Here the experiment results graphically represented here below. And now some conclusions. The energy consumption of MQTT protocol is highly different in case of using various quality of service levels. Therefore, the developers of Internet of Things system should choose the most appropriate quality of service level by taking into account the requirements of reliability, latency, and energy needed to perform communication with respect to the battery life. On the basis of our experiment results, we can evaluate the difference in energy consumption of 3 MQTT protocol quality of service levels. And finally, the main results are as follows. Using MQTT protocol for Internet of Things communication, the results of our experiment can be used for energy consumption prediction, what is we think very important, of 3 quality of service levels. At least once consumes 29% more energy than at most ones. Exactly once quality of service level consumes 87% more energy than at most ones. And finally, exactly once consumes 45% more energy than at least once. So thank you for your attention. Maybe some questions.
Thank you for your presentation.
Thank you.
Discussion, please, questions. So I have question. What sequence of the experiment are you used? What steps were performed?
Okay. As I mentioned, some steps back here. We used the digital voltmeter with quite large memory. About 65,000 measurements were stored for every step of our experiment. At first, we turned on the quality of service 0, and for 3.5 hours, every 200 milliseconds, we fixed and stored the voltage of our battery. And then battery was again charged, and we repeated the second step for the other quality of service, and so on. And then we found out the decreasing of battery, as you can see here, of battery voltage for every quality of service, and that's why the conclusion were made out.
More questions? Thank you for your presentation.
Thank you.
So the next presentation will be Syed. Vehicle license plate detection and perspective rectification.
Thank you. My name is Syed Haider, and I'm from King Saud University, Saudi Arabia. So today I'm going to present our research titled Vehicle License Plate Detection and Perspective Rectification. The outline of my presentation is as follows. I will start with a brief introduction. Then I'll talk about the detection algorithm of the license plate, followed by the perspective rectification, and then I'll talk about the algorithm for the license plate cropping and some of the pre-processing steps which we have used. Then I'll talk about the results, and finally the comparison of the proposed method with the related work. As we know that the character segmentation and perspective rectification of the license plate is very important in many applications, including traffic monitoring, car parking, if we have to recover the stolen vehicle or any toll payment. And the character segmentation and perspective rectification, they have a considerable impact on the precision of the license plate of the vehicle identification. Now VLP recognition is quite challenging because of the many issues, and like sometimes the captured image is already rotated, and sometimes there is too much noise in the image. Well, we have in the developed countries already there are many systems which are already implemented, and still some people are doing research. And in the vehicle images, VLP seems tilted sometimes in the horizontal or vertical direction or a mixed tilt, and the tilt and rotation correction of the VLP is very important for the overall identification system. So this is the detection algorithm. We have the RGB image of the vehicle. First we simply convert it to the grayscale image, and then we find the gradient of the image. And how we obtain the gradient of the image? Like we obtain it by selecting a pixel, and we subtract the value of the grayscale pixel from the neighboring value, from the grayscale value of the neighboring pixel. For instance, if we are selecting a neighboring pixel in the same image row, then the resultant will be the directional derivative in the horizontal direction. Similarly, if we are selecting a neighboring pixel from the same image in a column, then we will get the directional derivative in the y direction. So once we have this gradient, and the value of the gradient image, if it is high, that means there is a edge or a sharp transition from a lower value of the grayscale to a larger value of grayscale. Once we have this gradient image, then we are applying the filtering to the gradient image in the horizontal direction, and we are convolving the gradient image with the impulse response of the filter, and the height of this filter is the same as that of the actual image, and the width is actually based on the approximate size of the object which we are going to detect. So, and we are setting a certain threshold, and once the convolved image is available, then we set a certain threshold, and there is a transition from low threshold to high threshold. Then we will find the left edge, and similarly, if we have the high to low transition, we'll get the right edge. We can see that there might be some noise in the license plate area, which is the area of interest. Then we are selecting the maximum possible distance from the left edge to the right edge. So similarly, we are doing the vertical filtering, and for the vertical filtering, again, now this will be the input image, and we will apply the convolution with the impulse response of the filter again, but this time we will be having a different width because here the area of interest is reduced. Now this is the main part, which is the perspective rectification. The image of the vehicle can be captured from many directions. Sometimes the image is captured, the captured image is already rotated or tilted, and it results in difficulty in recognition of the license plate. Mainly there are three possible ways. One is the horizontal tilt, vertical tilt, and mixed tilt. Sorry. So here we can see the example of a horizontal tilt when the angle of alpha is greater than 0. Here the angle alpha is less than 0. Here we have the license plate tilted in a vertical direction, so we have beta greater than 0, beta less than 0. Similarly, here is an example of a mixed tilt. Usually researchers are using the planar homography method, and it is a very well-known technique which is applied for correcting the perspective rectification of the camera. So the main important thing here is to find the 4 corner points of the license plate. Now in the literature review which we did, we found that there are few articles in which they did the manual selection of the corner points, and then they are doing the planar homography. Once we know the 4 corner points, then we will perform the we'll have the homography matrix, and it is like a 2D to 2D transformation. So each pixel from the actual image will be shifted to the new position based on the homography matrix. So this is the algorithmic flow for the license plate sorry, for the license plate dropping. So here we have by applying the license plate detection, we have already extracted this license plate. As we can see that it is already tilted a little bit, so we convert it to the grayscale image, and then we apply some morphological operations on this image, and we'll get this binary image in which the area of interest is white pixels and the background is black pixels. Then we extract the boundary of the license plate, and from this boundary we actually detect the abrupt changes across the boundary. So for example, if we see here, what we do is we note the row pixel of the complete boundary, and then we did the cumulative sum, and then we detect the abrupt changes. As we can see that there are 3 red lines here. That means we have 4 one abrupt change here, second abrupt change here, and the last abrupt change here. That means we have 4 segments, and each segment represents one side of the license plate. So what we do is we will take, like, if for example we have this complete range, so we get to the center of the point and we go 25% on both sides, so that will provide us the 2 points on that particular side of the license plate. Then we apply the linear polynomial, and we can see that the lines are intersecting at these points, so we'll get the 4 corner points automatically. Once we have these 4 corner points, we will do the homographic correction by applying the homography matrix, and finally we will crop the image. Here we have some of the basic pre-processing steps which we did. So again we have the actually this is just the next slide is just talking about from here to here, because we are just doing some pre-processing steps. Yeah, so first we do the adaptive histogram equalization to enhance the contrast of the image. Then we do the binarization, and we suppress the light structures that are connected to the boundary of the image, the border of the image. Flood fill operation. After that we are doing the closing operation followed by the opening operation. It will remove the most of the noise in the image, and finally we are doing the convex hull, which will give us the required binary image with the area of interest in white and the black pixels as the background. Now here are the results. In this work, what we did is that we have 2 kind of data sets. The first one is the simulation data set, and for that what we did is we have one image which we rotated in different angles and from different perspectives. So for example, that image, one image was tilted horizontally from alpha was varied from minus 40 degree to 30 degree, and there were total of 14 images. Well, the perspective was not changed here because it was not having an impact on the horizontal tilt. So there were total of 14 images, and all the images were correctly rectified. For the vertical tilt, we did the rotation angle from minus 60 degree to 60 degree with a perspective angle variation from 10 degree to 120 degree. So here also all the images were correctly rectified. Then we did the depth variation, and after the depth variation we did the horizontal and vertical tilt, and vertical and depth tilt also. So here the accuracy is slightly lower because we are performing like multiple rotations, like we are changing the alpha, beta and the perspective angle at the same time. So there were few conditions when the depth of the alpha and beta were more and the perspective angle was large, then the image was not. We will see one example when the image was not correctly rectified. So the overall accuracy we achieved was 97%, 97.16% for the simulated images. Here we are like for example, this image one shows the horizontal tilt. It was rotated at a 15 degree, and the correct homographic corrected image. Then this is an example of a vertical tilt in which the image the beta was minus 50 degree and the perspective angle was 100 degree. So similarly, from image 6 to image 8, they are the real captured images, and in this example, for example, we have the shadow also. So even though we are doing some morphological operation, still we are getting desirable result here. And for example, in this case the tilt angle looks very large, and still the result is good. Here we have a little bit distorted plate, but the algorithm is performing very well here. Now here are some results when the algorithm did not perform well. Now if we see here, the perspective angle is 110 degrees and the gamma is 40 degree, which is the depth. So here the problem was the binarization steps which we did. This part actually, when we perform the morphological operations, this part, the edges were truncated, and it results in the false slope, which resulted in 1 or 2 false corner points. So even if the image is like we consider these results as the false results, but still the license plate we can see is we can easily recognize the characters and we can do this character segmentation, but we consider these results as the incorrectly rectified images. And the actual reason for this, like for this image, if we see the binarization step, there is a truncation of the edges here, and which resulted in the false pair of points in this side, which resulted in a false line. So these two corner points are not according to where it should be. So this resulted in the slight variation in the results. So here is the comparison of the proposed method with the related work. Some of the works they did only the license plate extraction. Some of them has performed the tilt correction also. There is one article in which they performed the license plate extraction as well as the tilt correction, but in this they are doing the manual selection of the corner points. But in our case we are doing the automatic selection of the corner points. The problem associated with our work is that if the license plate is dented, like if the edges are not smooth, then this might fail, because when the edges are not smooth, then by applying the linear fitting, it might result in finding the different corners. And the second thing is that if the depth is too much, like if the angle of if the license plate is tilted too much, then it might not recognize the edges properly. So in conclusion, we applied the convolution based method for the license plate detection and homography based method for the tilt correction. We applied horizontal and vertical filtering for determining the horizontal and vertical borders. These borders are used for extracting the license plate, which may be tilted in various directions. We have applied some morphological operations and polynomial fitting for determining the 4 corner points, and these corner points are used for the homography equations. We have evaluated the performance using 1094 images. These are the simulated images in which the license plate were purposely rotated and tilted. We achieved 97% accuracy in the simulation results. Additionally, the accuracy was verified on the real captured images. We captured 150 real images with different backgrounds, and by applying our proposed method, these captured images, we achieved an accuracy of 95%. So that's the end of my presentation. If you have any questions.
For good presentation. So, questions? Yes.
In fact, I would have 2 questions.
Yeah, sure.
First, why haven't you used well-known approaches for corner detection like Harris method? Why haven't you used a Kenny line detector?
Yeah, actually we...
And the second question is, which method of binarization have you used? Is it an adaptive binarization like NeBlack or Salvo or some other methods, or just the use of outsutation?
Yes, normal binarization. For answering your first question, actually we tried different algorithms which are directly available for the 4 corner points detection, but we were not getting the, like for all of these simulated images, we were getting very bad results. Like it was giving the false corner points. So that is the reason we went to come up with something that is our own work, and we tried to come up with a method that we can automatically detect the corner point, because the reference which I am citing, they also use the manual yeah, here. So here this reference, the tilt correction based on straight line fitting method and projection, and what they are doing is they are this one, perspective rectification using 2D to 2D transformation of planar homography. So what they're doing is they are manually selecting the 4 corner points, because they were also getting the false results, not getting the accurate corner points.
Okay, but if you try to combine the morphological approach with Ken, with Harris, probably you will miss some problems you have.
Yeah, maybe.
Additionally, if you use adaptive binarization, you would have no problem with uneven lighting and so on. The use of just a simple offset thresholding will give you some problems like this, and if you try to use OCR engine to recognize your register plate numbers or some signs, probably it will also give you some problems, because your accuracy was much lower on natural images. So this is the reason. So maybe it could be just an advice.
Yeah, sure.
Okay, so that's all.
Thank you.
More questions? Thank you for your
Thank you.
presentation. And the last one presentation, Grega Urbančić, performance study of BAT algorithm running on embedded hardware.
Thank you, Mr. Chairman, for the introduction. So, hello everyone. My name is Grega Urbančić, and I'll present to you today our paper titled "Performance Study of BAT Algorithm Running on the Embedded Hardware." So, here's the short agenda of my presentation, which is structured as follows. Firstly, we'll go through the introduction and describe the problem which we are addressing. Then I'll present to you quickly the computational intelligence, more specifically the BAT algorithm itself. Then I'll present to you our performed experiments and the experimental settings. Afterwards, we'll take the results of the conducted experiments, and finally, I'll conclude my presentation with some final thoughts and possible future work. So daily, the majority of people is facing with many optimization problems unconsciously. So let's say, for example, when we deal with money, resources, or even when we travel around, we always search for those options bringing us the highest benefit. So basically, what we are doing, we are solving an optimization problem. So in the real world, we can easily make decision in order to find the best solution, especially when we have a lot of information about a particular problem. So simultaneously to this analogy, many scientists have been developing various algorithms for solving optimization problems that are based on the mathematics, physics, chemistry, or even biological principles. So the latest, based on the biological principles, one of them are also the stochastic population-based nature-inspired algorithms, which are in recent years quite popular and mimics the natural or biological systems by solving the optimization problems. So, what was the motivation behind this research? The stochastic nature-inspired population-based algorithms running on disembodied computers such as PCs, computer grids, and even cloud reach their mature phase. But with the expansion of IoT, wearable devices and such, naturally comes the question if it's possible to run such algorithms on less powerful devices. And secondly, can they achieve the results in an acceptable time? For the latter one, the acceptable time has to be defined, and usually the acceptable time is defined by the problem which we are trying to solve and the limitations of the problem. So in this research we focused on the first question. So computational intelligence. So recently there exist a lot of nature-inspired algorithms that are brought together under the umbrella of computational intelligence, or short CI. Some representatives of such algorithms are, for example, Firefly algorithm, BAT algorithm, particle swarm optimization, Grey Wolf optimizer, cookie search optimizer, and so on. What is common to all of the mentioned algorithms? every algorithm consists of set of individuals, or what is called the populations, and those populations secondly are governed by variational operators such as mutation, crossover, or selection. So the BET algorithm is the one which we used in our study. It was first introduced by Jinshi Yang in 2010. It's one of the stochastic population-based nature-inspired algorithms, and it's inspired by biological or physical phenomena, echolocation of microbats. So basically, what the algorithm is trying to mimic the echolocation of microbats. So bats are emitting the sonar signals in order to locate the potential prey or detect an obstacles. They receive the bounce back signals, and based on the bounce back signals, they are able to identify whether there is an obstacle on the or the prey, and even if the prey is moving towards them or away from them. So translated to the algorithm, the BET algorithm consists of the following 6 components. So at the beginning we have the initialization of the parameters of the algorithm, and initial population is conducted, while the evaluation determines the best solution in the population. So in next step, the virtual bats are moved in the search space according to updating rules of the BET algorithm. So next step is the best solution is being improved using random walks, and after that the evaluation of the new solution is achieved. Next step is conditional archiving of the best solution, and at the end the current best solution is updated, and then we go back to the second step and repeat the remaining 5 steps. So in order to properly evaluate the performance of optimization algorithm, there are commonly used so-called benchmark functions. So in our experiment we used those 10 well-known benchmark functions like Rastringin, Griwank, Rosenbrock, Eckley, Schraffel, De Jong, Isam, Mikhailovich, Jinshi, and Zakharov. So the purpose of our experimental work was to show that the used Raspberry Pi platforms are appropriate not only for running optimization algorithms, but also for the embedding the evolutionary and swarm intelligence algorithms into the hardware. So naturally the BA algorithm is implemented in C++ language, as well as all benchmark functions are also implemented in C++. I have to point out here that the same algorithm implementation was run on all of the tested devices, so there were no changes between implementation on each device. So in the following table are presented the devices running the BET algorithm against the benchmark functions. So in the previous research we only compared the performance of smartphone and PC running the BET algorithm, and this research extended the devices using the Raspberry Pi devices. So we have used first Raspberry Pi Model B revision 1. This is the very first Raspberry Pi device with single core processor at 700 megahertz frequency with 256 megabytes of RAM. And the second two ones, Raspberry Pi devices, are the latest one, Model B Plus and Model A Plus, using the Broadcom CPU, quad-core CPU at 1.4 gigahertz and 1 gigabyte RAM, and the last one has the 512 megabytes of RAM. All of the Raspberry Pi devices are running Raspbian OS. So the following are the BET algorithm parameter settings. So the first parameter describes the dimension of the problem. The second one is for the number of the population. The third one sets the number of runs of each benchmark function, and the fourth one is the number of generations. So eventually in each generation there is performed 10,010 function evaluations against each benchmark function. And the last 4 parameters are specific to the BET algorithm, which represents the signal loudness, pulse emission rate, and the minimum and the maximum frequency. So the results, the quality of the results was measured according to the time needed for execution of all the number of runs. Of course, the lower the time complexity, the better the observed algorithm is. In the paper, we presented the minimum, maximum, mean, median, and standard deviation of time values. But for the purpose of this presentation, I'll only focus on the mean time values. Logically, the PC and smartphone performed the best. The PC exposes the best results in the sense of the minimum time complexity. BA running on the smartphone is around 10 times slower than on PC, but focusing on the Raspberry Pi platforms, we can see the progress made from the revision 1 Raspberry Pi to the latest revision 3, which is around 4 times less time complexity, which is quite nice improvement. But most importantly, comparing the Raspberry Pi revision 3 B plus and A plus, we can see that A plus, even though if it has the less memory than B plus, performs better than the Raspberry Pi Model B, which has 1 gigabyte of RAM. So here is the graphical representation of the results of the conducted experiments. So at the bottom line we can see that there is smartphone and personal computer. The highest one is the Raspberry Pi revision 1, and the yellow and orange lines are the revision 3 Raspberry Pi platforms. To conclude, we try to solve the classical global optimization problems on specific Raspberry Pi devices that serves as hardware platforms for embedding the evolutionary and swarm intelligence-based algorithms. Raspberry Pi devices are capable of running the stochastic natural inspired population-based algorithms. The results of the same quality as on regular PC can be obtained on these devices, but in a slightly longer time. Regarding of the problem which we are solving, we have to say if it's okay to run this slightly longer time, or if it's not acceptable. For the further development of such devices could ensure the stable infrastructure for using in evolutionary swarm robotics. So based on those encouraging results, we would like to extend our work to use optimization of stochastic inspired population-based algorithms in terms of time complexity, so to maybe achieve somewhat the same level of performance in smaller time complexity, and to conduct experiments with other popular algorithms such as Firefly or particle swarm optimization. So thank you for your attention.
Thank you for your presentation. Let's start discussion. Questions, please. I have a question.
Yes.
One of your algorithm step was with randomization.
Yes.
Could you say randomization in various hardware take place to your result evaluation or no?
Yes, for that matter we repeated each experiment 25 times, so we could eliminate the randomness factor on each hardware devices. So those are the averaged results on the 25th runs.
So there was average result. And the next question is Raspberry B and A.
Yes.
B results were were better. Yes.
Yes.
You mean is for RAM?
Yes.
Yes.
We are looking those the revision 3 Raspberry Pis. Yeah.
1 giga. Yeah.
Yeah, no, this one has 1 gigabyte of RAM and this has only 512 megabytes of RAM, but the same processor.
But
yes, but the lesser the computational time complexity. Yes, that's quite interesting. Maybe because of the different how it said release of the Raspbian OS, we didn't expect it so much in depth. Why this happens? But maybe because of the different build of the Raspbian OS, because it's the slightly different hardware than the Raspberry Pi B Plus revision 3.
Operating system, you mean?
Might, yes.
Okay. More questions?
If I understood, you're analyzing stochastic systems, yeah?
Excuse me?
Stochastic systems you're analyzing.
We are just trying to prove if it's possible to run the optimization algorithms on embedded hardware.
But if you are using Monte Carlo method, for example.
Excuse me?
Monte Carlo method, you know?
Yes, I know, but we didn't use it on the experiment, yes.
More questions? So, thank you for your presentation.
Thank you.
Thank you all for our session. Our session is over, and we will now have lunch.